So this lecture covers the topic of chemical kinetics, which is how quickly or slowly a chemical reaction occurs and ways that we can change the rate of a chemical reaction. And this is the first of our last 2 units of the year. All right, so when we were learning about balancing chemical equations, we did a molecular workbench activity that explored factors that affect the rate of reactions, along with looking at the law of conservation of mass and matter. And that activity introduced you to what's called collision theory. And basically, what collision theory says is that in order for atoms, molecules, and ions to react to form products, they have to run into each other. And they're only going to run into each other if they have enough kinetic energy and if they're oriented in the right way for that to happen. So the minimum amount of kinetic energy that's needed for a reaction to occur is what's called activation energy. And we're going to look at that on the next slide. And the reaction rate, or rate of a reaction, is how the amount of reactant is changing per unit time. And we usually look at that in seconds. Okay, so this slide right here represents the process or progress of a chemical reaction, and it's what's called a reaction profile. Now, this one's not real quantitative, but it definitely gives you the idea of what's happening. So right here you have your reactants. So letter A represents the reactants, the boulder. And in order for the reactants to be converted to products, which are over here, you have to push them to the top of this hill. And the top of that hill, or the height of that hill, represents what's called the energy of activation or activation energy. Either one, they're the same thing. Okay. So in order for reactants to be converted to products, you have to overcome this activation energy. And we'll be looking more at reaction profiles in our last unit of the year, which is thermodynamics. All right, so there's ways that we can impact the rate of a chemical reaction. One of the ways that we can impact reaction rate is by temperature. Another way that you can impact reaction rate is the size of the particles. A third way is concentration, and the fourth is with use of a catalyst. We're going to explore each one of these and how they impact collision theory separately. All right, so temperature and reaction rate. If you increase the temperature, you're increasing how often collisions occur and the number of particles with enough energy to slip over the activation energy hill. So in other words, you've got particles moving faster, they're colliding more, because that's what temperature is actually a measure of, is the measure of the average kinetic energy. So if temperature is higher, particles have more kinetic energy. So there's more particles that have enough energy to slide up over the hill, and they're going to run into each other more often. This slide shows the impact of concentration on reaction rate. So what happens when you increase concentration is that you have more particles in a given space. And that's actually illustrated pretty well in this picture. Notice that you have more of both types of atoms reacting. Because there's more of them packed into the same amount of space, they're more likely to run into each other. So when you have a high concentration, you're going to get more collisions than you would if the concentration was low. And that, therefore, when you have more collisions, the reaction rate is going to be higher. Another way to impact reaction rate is by adjusting particle size. And these pictures actually show it well. And this is a reaction between hydrogen chloride and magnesium. And the green illustrates the magnesium. And the red are hydrogen ions that come from the HCl. So what you should notice here is that in the top diagram, the hydrogen ions can surround the piece of magnesium, but they can't get to the middle. Versus when you take the magnesium and you break it up into smaller pieces, so you've increased its surface area, the hydrogen atoms can get to the middle of it. They can pretty much surround lots of magnesium rather than just one big lump. So when they can surround it more, there's going to be more collisions. Okay? So a great way to adjust particle size is you could dissolve the reactant and so let the reaction happen in solution, or like this picture shows you, grinding the reactant up or cutting it into really tiny pieces. The last way to impact reaction rate is to use what's called a catalyst. And a catalyst is something that increases the rate of reaction, but it's not a reactant itself. So it isn't consumed in the reaction. You can tell a reaction has a catalyst in it if, when you look at a chemical equation, and I'll just use the one that we were just looking at as an example, and you see something written above the arrow. Sometimes the catalyst could be a substance, sometimes it could be heat, sometimes it could be any number of things, okay? But these are written along the arrow because what they they're not actually involved in the reaction, they're regenerated in the process. Okay. But the way a catalyst works is it lowers that activation energy barrier that we looked at a few minutes ago. So the blue pathway here represents the pathway that a reaction would follow if there was no catalyst. And notice that here's the height of the activation energy. It's pretty tall, pretty big. If you do the same reaction but you add a catalyst, that reaction or that activation energy hill becomes much lower, and so it takes less energy. So less energy generally means it's easier. It's going to happen more easily. Great example of use of catalysts is actually in our bodies. Our bodies use proteins, special kinds of proteins called enzymes, to catalyze many important reactions that would normally go really slowly or not at all on their own. And a great example there would be like amylase, which is in your saliva, which begins the digestion process, actually. And you may or may not have done a lab activity with some amylase. Another enzyme that I can think of off the top of my head is one called catalase, which is in our red blood cells. And catalase, we actually see evidence of catalase when we look at and we use hydrogen peroxide. It's catalyzing or speeding up the reaction of hydrogen peroxide being decomposed. All right, so that about wraps this one up. What we'll be doing with this in class is we're going to be doing a lab activity investigating whether or not the reaction rate can be affected by these factors. So actually verifying that, yes, they do hold true.